Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to help you figure out how to calculate the mass defect and the nuclear binding energy of your nucleus per nucleon. Okay, so mass defect. Mass defect is basically the difference in the mass between, if you were to add up all of the nucleons in your nucleus, all the protons and neutrons, all their masses, add up all the masses that are there, and then compare that to the actual mass of the isotope itself, all put together, right? So it would be the same thing as if I took all the bricks off of a wall, measured each individual bricks, and then got the total mass of all the bricks together. And then when I put the bricks together in a wall, I took the wall and found the mass of the wall, and I found a difference in the mass. That would be strange, right? Well, in nuclear chemistry, in the nucleus, you may have heard of this famous equation equals mc squared. Well, basically, what is going on is that difference in the mass, you'll find that the mass of the nucleus, when it's put together, actually has a slightly smaller mass than when they are separated from each other. And that is to say that some of that mass was converted into energy that is used to bind everything together, right? So you have these protons, right? These protons that are positively charged, right? Positive charges don't like to be next to each other. They want to repel. So what is keeping them together? Well, it's that binding energy. And so that is what we refer to as the mass defect. Okay, so that mass defect is the mass that has been converted into binding energy to hold the nucleus together. And then we're going to find out, well, how do you figure out the binding energy per nucleon? Okay, so let's start with our first one. Carbon 16, we're given the mass of a carbon 16 isotope at 16.014701 AMUs. And so, sorry about that. And so, what we need to do is figure out the total mass of each nucleon in here. So, we have carbon is 6 protons. So that means for this carbon 16, we have 6 protons and the rest is neutrons. So neutrons. So we have to add all of that together. So let's look this up. So we have the mass of, let's see, a proton, which is hydrogen. So we have 6 times the mass of hydrogen. So, and that's going to be plus, plus, we got 10, and we're going to have the mass of a neutron, so that's 1, 0. That's the symbol for a neutron, symbol for a proton, which is basically a naked hydrogen atom. It's the hydrogen nucleus without the electron. And we're going to have to subtract out the mass of our carbon 16. So let's see, how should I write that? Oh yeah, the mass of carbon 16. And so when we do this, we put in the mass of our nucleus of the proton, 1.00, 783 AMUs. Okay, we're going to add to that 10 protons. So we have neutrons, and the mass of neutrons 1.00866, 1.00866. Let me double check. 866 AMUs. And we're going to subtract out the mass of our C16, which is this right here. So we subtract this out. So 16.0144701 AMUs. And when we calculate this out, we get a difference in the mass. And that difference in the mass is 0.00866. So 0.118879. 8879. We're only allowed up to here since we're adding. So we're only up to 5 decimal places, but we're keeping 1 to avoid rounding error. So this is a mass defect. Mass defect. So this is the amount of mass that's missing. So when we add these together, when we add our 6 protons and our 10 neutrons together, we should get this amount more. This is what we get. But when we put it together, from here, we're missing that amount. That's the amount of mass that was converted into binding energy. So now we need to figure out the binding energy per nucleon. They want us to find the binding energy per nucleon in mega electron volts. So let's go ahead and do that. So we're going to take this and we are given, let me make sure I write this down correctly, 931.5. So 931.5 mega electron volts is equal to 1 AMU. So all I need to do is take this, this is in AMUs. All I need to do is take 0.118879 AMUs and then multiply by this conversion factor. So 1 AMU on the bottom and 931.5 mega electron volts on top. AMUs cancel. And so now I got my mega electron volts. I calculate that out and I get 110.74. So I get 110.74 mega electron volts, but that is not per nucleon. That is the total for the missing mass defect. So this mass was converted in this much energy, and so now I need to get this energy per nucleon. How many nucleons do I have? I have 16. 6 protons, 10 neutrons. So I'm going to divide this by 16, and then I get the final answer of 6.921. So the answer is 6.921 mega electron volts per nucleon. So that is the binding energy per nucleon. Okay, let's do the second problem. Okay, so for the second problem, we have U-238 mass is equal to this number here. So again, first thing we want to figure out is what's the difference in the masses of all of nucleons related to or compared to that of the total mass of one isotope atom. So what we need to do is we're going to find the difference. So the mass defect, again, here is going to be equal to the mass of the neutrons plus the protons. So we need to figure out how many protons we have. So we got to look up uranium. I believe it's 92, but always best to verify. Yeah, 92. So we have 92 protons, and then the rest is neutrons. So we subtract out 92 from 238. It's going to be, let's see, 138 plus 8, 146. So we have 146 neutrons. Okay, so now we got to add these together. So we're going to have 92 times, again, the mass of the proton. So it's going to be hydrogen, which is 1, plus 146 neutrons minus the mass of uranium-238. So we put these numbers in. So 92 times, again, I gotta look this up. Shouldn't have erased it. 1.00783, 1.00783 AMUs plus 146 times 1.00866, 1.00886 or 866, 866 AMUs, and then subtract from that the mass of this isotope, which is right there, 238.0507784 AMUs. And then we calculate that out. And the difference is 1.6339. 1.6339. Oh no, sorry, I'm sorry. 1.9339. That should be 1.933936. Again, only allowed up to there for our decimal places. All right, so now we have, this is AMUs, this is the mass defect. This is the difference in the mass of the total protons, neutrons separated versus when they're put together in the nucleus. So this is the amount of mass that was converted into binding energy. So now we need to convert this to mega electron volts. So again, we're going to use this conversion factor here. So 1 AMU on the bottom and 931.5 mega electron volts on the top. AMUs cancels out, and we get, what do we get? Okay, we get 1801. So 1801.46138, 46138 mega electron volts. Again, that's the total amount of energy, but we want the energy per nucleon. So we're going to have to divide it by the total number of nucleons, which is 238. So we're going to divide this by 238. And we get, divided by 238 equals 7.569. So we get, I'll write it over here, 7.5. Here we go. 7.5691 mega electron volts per nucleon. So that would be the binding energy per nucleon for this uranium isotope. Hope this was helpful. If you like my videos, please like, share, subscribe, hit the notification bell, and put a comment in the comment section. I'll see you next time. Thanks for joining me.